Hello, students. Have you ever really stopped to wonder what makes something like gold so different from, say, iron? Or how these huge nuclear power plants can generate so much energy? Well, the answers to all these questions, they lie deep inside the tiny, tiny atom. So today, we're going to unlock some of those secrets. We'll be exploring atomic number, mass number, and the really fascinating world of isotopes and isobars. Trust me, getting these basics right is the absolute key to understanding all of chemistry.
So, here's our plan for today. We'll start with a quick look at the atom's core particles, just to refresh our memory. Then, we'll discover what gives an atom its unique identity and figure out how to weigh it. After that, we'll meet the interesting atomic family of isotopes and their lookalikes, the isobars. And finally, we'll wrap it all up with a quick recap to get you perfectly ready for your exams. So, shall we begin?
Okay, first things first, let's just take a moment to refresh what we already know. What are those tiny little particles that make up every single thing around us? Right, so every atom is made of three fundamental particles. First, we have the protons, which carry a positive charge. Then there are the neutrons, which are neutral. They have no charge at all. Now, these two, the protons and the neutrons, they are packed together right in the center of the atom in a very tiny, dense area that we call the nucleus. And then revolving around this nucleus in their own special paths are the negatively charged electrons. Now let's move on to our first new topic for today. How do we tell one element from another? I mean, what gives an element its special identity? Just like you have your very own roll number in your class. Let's find out. Well, an atom's identity, it's all defined by its atomic number. We represent this with the letter Z. And the definition is actually very simple, but it's so important. The atomic number is just the total number of protons you find in the nucleus. That's it. Not the neutrons, not the electrons, only the number of protons. And this number is completely unique for every single element. Let's take the simplest example we have, hydrogen. A hydrogen atom has just one single proton in its nucleus. So its atomic number, its Z, is 1. See? It's that simple. Okay, how about another one? Let's look at carbon. Now, a carbon atom has 6 protons in its nucleus. So what do you think its atomic number will be? You got it. Its atomic number, Z, is 6. So the main point to remember is, if you know the number of protons, you know the element. Period.
Excellent. So now that we know how to identify an atom, let's figure out how we measure its weight, or to be more accurate, its mass. You see, almost all the mass of an atom is concentrated right there in its nucleus because electrons are incredibly, incredibly light. And since the nucleus has protons and neutrons, we calculate the mass number, which we represent with the letter A, by simply adding the number of protons and the number of neutrons together. In fact, these particles in the nucleus, the protons and neutrons, are often called nucleons. So really, the mass number is just the total count of nucleons. And calculating this mass number, it's as easy as simple addition, really. Step 1, find the number of protons. Step 2, find the number of neutrons. And for step 3, you just add them up. That sum is your mass number, A. Now in chemistry, we have a standard way to write all this information down. Let's take nitrogen as our example. Its symbol is N. The mass number, A, is written as a superscript. That means it goes on the top left. So in this case, it's 14. The atomic number, Z, is written as a subscript, so it goes on the bottom left. Here, it's 7. So just by looking at this, you immediately know that a nitrogen atom has 7 protons and a total of 14 nucleons. That is, 14 protons and neutrons combined. Okay, now we're going to move to a really fascinating idea. We said that the number of protons is what defines an element, but what if atoms of the same element have different numbers of neutrons? Well, this gives rise to a special kind of atomic family, which we call isotopes. So, what are isotopes exactly? Well, they are atoms of the very same element. And if they are the same element, what does that mean? It means they must have the same number of protons, and so the same atomic number, Z. But, and here's the twist, they have different numbers of neutrons. And since the mass number is protons plus neutrons, it means isotopes have different mass numbers. It's important to know that because they have the same number of protons and electrons, their chemical properties are almost identical. They react in the same way. Let's try to understand this with the family of hydrogen. You can think of them as 3 brothers. The first brother is called protium. This is the most common type of hydrogen you'll find. It has 1 proton and 0 neutrons, so its mass number is 1. The second brother is called deuterium.
It also has one proton, of course, but it has one neutron as well, so its mass number is 2. And the third brother is tritium. It has one proton and 2 neutrons, giving it a mass number of 3. See? All of them are hydrogen atoms because they all have one proton, but they just have different masses.
Now, this brings us to a very common question that students often ask. If you go and look at the periodic table, you'll see that the atomic mass of chlorine is listed as 35.5. It's a decimal number. But how can that be? The mass number is the sum of whole protons and whole neutrons, right? So how do we get a decimal? The answer is isotopes.
The reason is that if you take any sample of chlorine from nature, you'll find it's actually a mix of 2 isotopes. About 75% of the atoms are chlorine-35, and the other 25% are chlorine-37. So the atomic mass you see on the periodic table is a special kind of average, a weighted average, based on how common each isotope is. To calculate it, we take the mass of the first isotope, which is 35, and we multiply it by its abundance, which is 75%, or 75 by 100. Then we add that to the mass of the second isotope, 37, multiplied by its abundance, 25%. When you do the math, you get 26.25 plus 9.25, which gives us a final average of 35.5 atomic mass units. And that's the secret behind the decimal.
You see, isotopes are not just some topic in a textbook. They are incredibly important in the real world. The electricity that might be powering your home right now could be coming from a nuclear reactor that's fueled by an isotope of uranium. Doctors use an isotope of cobalt to fight cancer, and an isotope of iodine is used to treat thyroid problems like goiter. So you see, isotopes are all around us, doing some really amazing things. Okay, now that we have a good grasp of isotopes, let's learn about another term. It sounds a bit similar, but it means something quite different. Let's talk about isobars.
So what are isobars? Well, isobars are atoms of different elements that just so happen to have the same mass number. This means they have different numbers of protons, so they are different elements, but the total sum of their protons and neutrons is the same. They're like lookalikes when it comes to mass, but they are completely different elements with different properties.
Now, I want you to pay close attention here, because telling the difference between isotopes and isobars is a very common exam question. Let's break it down. For isotopes, I want you to remember the P in isotopes stands for same protons. They have the same atomic number Z, but a different mass number A. They are atoms of the same element. Now for isobars, think of the A in isobars standing for same A, or same mass number. They have a different atomic number, but the same mass number. And they are atoms of different elements. A perfect example is argon and calcium. Both have a mass number of 40, but they are totally different elements. Argon has 18 protons, while calcium has 20.
All right, that was quite a bit of new information, wasn't it? So let's just quickly go over the most important points from this lesson, the things you absolutely must remember for your exams.
Okay, let's lock in these key points. Atomic number, Z, is simply the number of protons. It's the atom's identity card. Mass number, A, is the total of protons plus neutrons. Isotopes have the same Z, but a different A. Isobars have a different Z, but the same A. And here is a very useful formula for your numericals. If you need to find the number of neutrons, just subtract the atomic number from the mass number. That is, A minus Z. Please make sure you revise these definitions very well.
Let's finish with a little challenge to test what you've learned. Imagine we have two atoms, X and Y. Atom X has 6 protons and 6 neutrons. Atom Y has 6 protons and 8 neutrons. So the question is, what are their mass numbers? And what is the relationship between atom X and atom Y? Are they isotopes or are they isobars? Take a minute, think about it, apply what we've learned today, and write down your answer. Great work today, everyone!